All right, good morning. Happy Thursday. Last class for us together this week. Where is everybody? What happened? Look back here. Look at all these empty seats. You just had enough, huh? Can't take any more. Yeah. By the way, we are on the downside of the semester now. I checked. I think this is the first lecture of the second half, I think, if I remember correctly. So it's all downhill from here, maybe in a good sort of way. Who knows? All right. Let's see. So today we are going to finish up or come close to finishing chapter 6, which is going to be the last of two topics dealing with sort of advanced force problems. Okay, so we did the situation where we have multiple connected objects, which was more of the same, just sort of a lot more of the same, right? It's like you have two objects, you have to deal with free body diagrams for both. The second thing that we're going to do is revisiting circular motion. Way back in chapter 3, we talked about the basic concepts about accelerations that make the velocity change in terms of the magnitude and the direction, which makes it go in a circle, okay? We are gonna focus on one of those here. The uniform circular motion is when the magnitude of the velocity is constant. So it's traveling in a circle, it's changing directions the whole time, but it's not speeding up or slowing down. It's just going around in a circle at a constant rate. And you might remember that we had an acceleration still in this particular case, which was known as the centripetal acceleration. This was the acceleration that specifically changed the direction. It just consistently changed the direction as it travels around in a circle. Does anybody remember what this was equal to? Yeah, v squared over r. It has that constant magnitude. And does anybody remember which direction this pointed? Yeah, direction always to the center of the circular motion. So we talked about the acceleration part of this. We now understand that acceleration is caused by an influence that we know is a force, and we have new equations that connect the acceleration to their force in the form of Newton's second law. So we've had Newton's second law in the x direction, and we've had Newton's second law in the y direction. It turns out that now we're going to have a new direction. And we are going to call this the c direction. And you might guess that the c direction is always to the center of the circular motion. The c direction always points to the center of the circular motion. So this is kind of a weird sort of direction, okay? Because at the start of x or y, we just said like, oh, let's say x is horizontal and y is vertical, they're perpendicular. Sometimes we tilt those axes, but we keep them perpendicular to each other. The c direction is kind of a variable direction in that you can imagine if I'm standing here just walking in a circle, right? Well, where the center of the circle is always sort of right here. But you can imagine if I'm pointing to the center of the circle, the direction that I'm actually pointing is changing, right, from your perspective. So the c direction is changing because where the location of the center of the circle is changing. That is, unless you're me. Think about which way that I'm pointing the entire time I walk in the circle. It's always to my left side the entire time. So from my perspective, the direction to the center of the circle is a constant. It's always to one side of me. That's not going to be changing as long as I'm traveling in a circle. So from two different perspectives, the c direction appears a little bit weird, which I think is what makes this a little bit hard for people, okay? So we're gonna basically spend all class today dealing with the c direction. Let me point out that we're not going to be adding a third dimension. We're still just going to be working in 2 dimensions. So my c direction in a given problem, we'll either replace the x or replace the y. We're not going to have x, y, and c all in the same problem. Okay, so you still only have to work in 2 dimensions. Here's the way this is going to work. Just like before, we had sum of the forces equals mass times acceleration. It's just now we're going to have a subscript c instead of a subscript x or y. So this is going to be consistent with everything we've done so far. The problems and the way that you proceed through the problem is exactly the same. You even start with the same equation, just with a different subscript, okay? The thing is, now I'm not going to have a 0 or an unknown value for the acceleration. I'm always going to have v squared over r, which is kind of nice, okay? If something is moving in a circle, this will be one of your equations, and the acceleration is always known, okay? Are we all right so far? Maybe a little bit? You're like, I don't know, you haven't shown me anything yet. You're gonna be okay. It's gonna be okay. Here's the thing. There are 2 terms that float around that tend to cause a lot of confusion. 2 terms that cause a lot of confusion, and because they're so confusing, it's not that they're completely illegitimate. There's some understandings that work for them. But from our standpoint, all they do is just throw people into a state of just complete and utter confusion. And I want to be consistent with everything that we've learned so far and sort of use the same terminology, okay? So these are 2 terms that we are basically never going to use. The first one of these is the centripetal force. Centripetal force, just cross that out. We are not going to do it. Not that we're skipping it, it's just that literally you are not allowed in this class to use something known as the centripetal force. The reason for that is there's not one. It doesn't exist. There is no such thing as a centripetal force. Meaning, in our list of forces, we had gravity and normal and friction and tension and spring. You can't add this to the list and say, ooh, I've got a new force. It's called the centripetal force. No. Never, please, I beg you, don't. Got it? Never, never, never. Okay? So this should never be in a free body diagram. Or problem anywhere. I should never see a reference to a centripetal force in any problem that you ever work in here, okay? Now, if you're thinking, but it's in the textbook, but I've seen it written in problems. I've seen the term used. I've seen things described as centripetal forces. Let me tell you what it actually means. This thing that's called the centripetal force is actually the entire left side of Newton's second law. In the c direction. So this whole thing, sum of forces in the c direction, is what's referred to as the centripetal force. And you can tell that, well, no, it's the sum of forces. It's not a force. It's the sum of forces that we already know about. On the left side, I could have any of the 5 that I've learned about. Gravity, friction, normal, tension, spring. Any of them can be over here. When I add them all together, and maybe I have a big long equation that has all these forces added together, all of that combined is what people call the centripetal force. So already we can see it's not a single force, it's comprised of all these other forces that I know about. It's not something on its own that acts, okay? So centripetal force, don't use it, ever, okay? The other thing that you're never going to use is another similar and common term, which I can't write, the centrifugal force. Again, don't. Okay, centrifugal force. The reason why you're not going to use this one is also because it doesn't exist. in and of itself. The centrifugal force does not exist. So also, never use it. Ever. Please. Thanks. There we go. The centrifugal force is what is known as a fictional force. We all know what fiction is. It's a story. It's made up. It's something we tell ourselves. And in this particular case, it literally is a force that's fictional, that's invented to explain something that's happening, but not because of a force. Allow me to go back in time just a little bit. Boy, that'd be great if all of a sudden I just went and just said the whole thing again, but I can't do that, sorry. I don't have a TARDIS. I wish I did. That'd be fantastic, but I don't. Let's see, so chapter, I don't remember now, early chapter 5, we talked about Newton's first law, okay? And we said that objects that are in motion, in a constant state of motion, or at rest, just want to stay that way. And it takes an outside force to come along and change that. Except in certain situations. Remember we talked about the airplane. And if the airplane's accelerating, then Newton's first law all of a sudden isn't working anymore because things can move without any forces, right? You put the coffee on your tray table, and no one comes along and says, coffee in your lap, but instead the airplane accelerating by itself basically leaves the coffee behind, is one way to think about it, right? It's sitting here, it would like to continue at a constant velocity, and now the airplane starts speeding up, and it just keeps going at a constant velocity, which means it ends up in your lap, okay? Sad thing, nothing touched it, there were no forces. If we were to invent a fictional force there, maybe we would describe something known as the airplane force. The airplane force is this weird force where nothing touches it, but it throws things in your lap. That would be a fictional force to explain a real phenomenon. The thing is, what's really happening, we understand, is Newton's first law. It's just trying to keep doing what it's doing, and as a result of that, it ends up looking like something pushed it. Okay? That's what's happening with the centrifugal force. It's a similar situation. There's acceleration. If we were all in a car, thank you all for being in my car. This is a lovely car. We're driving this way, okay? And then I'm going to turn very unexpectedly, and something's going to happen to all of you. So when I turn, I'm going to turn around and look at you, and you should all be doing, playing along with what happens. So I'm going like this, like that. And then I look back here to see what's happening to you all, and you're all sitting there just like normal. Why won't you play along? You will this time, right? I don't believe any of you. Okay, here we go. Okay, some of you are leaning a little. Which way are you leaning? You're all leaning this way, right? Okay, so all of you are like, like that, because I was going really fast and I turned really sharp. Now, what did not happen is it's not like everyone sitting to the side of you was all of a sudden just like, he turned to the left. That means I have to push you, like that, right? That did not occur. There was no force. Nothing pushed you. I didn't all of a sudden turn around and be like, all of you, like lean over. No force. It's fictional. That feeling like you got shoved to the right when I turned left is what people call the centrifugal force. But what is it really? Why did all of a sudden you feel like you went that way? Yes. You're just trying to keep going straight, right? You were going like this. And now the car decides to go over here, and you just keep going that way, right? So the car moves over this way, and all of a sudden you find yourself farther to the right in the car. If the door wasn't there, where do you go? You keep going straight, right? It's like you just keep going like this. Now the car goes that way, and you just keep going, which means you just went out the door, okay? Which is sad. It's good that we have a door there. That thing that's not pushing on you because of the result of Newton's first law is this made-up fictional force called the centrifugal force, okay? Both of these are misnomers in a way, okay? The second one just doesn't exist at all. It's not there. It's made up. The first one is describing more than just a force. It's describing the sum of all the forces in the c direction. So it's just the result of other forces, not a force in and of itself. So neither one of them ever use it, okay? So if I'm like grading papers and I look down through there and all of a sudden it's like I see F sub c, which could be either one of these really, and then like an arrow pointing some direction, I'm like, Then I just rip that page off and I go like that. And then what do? And then I take it all back out of the shredder, I make it into a little ball and I throw it at you. It's fantastic. I should do that. That sounds like fun. No, I'm not going to do that. Don't use these, please. Okay? So let's do a problem. Let me show you how this C direction works. And it's different, but at the same time, it should really be familiar to you right now because we're going to follow the exact same things as before, including our friend from earlier in this chapter. I think the only difference is that they replaced their attachment. Apparently their hands are replaceable. Previously they had a spring attachment here, and now they've decided to replace that with a simple rope attachment. Who in the world knows what might be next? No way to know. So this person has a rope, and maybe we pretend that they come running from the back of the classroom. They're going this way, and then they like sling the rope up and it connects to the top of the pole, and then they're like, whee, and they go swinging around the pole like so. So that they make maybe a circle that looks kind of roughly like that, okay? This is a still shot of with them when they're directly to the right of the pole. Got it? Okay? We're going to assume that they're able to just like keep swinging at exactly that angle for a little while and everything is just happy and they're having all sorts of fun, right? There we go. That indicates fun. They're a little blurry, but they're having fun, okay? So, a few different things. First of all, the circular motion that they're making, where is the center of that circle? I hear at the pole. Where on the pole? Tell me when to stop. I feel like there should be a greater reaction. Like I should almost feel like I hit something as I went through there because it's like, yeah! 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 No, so right there is the center of their circle, okay? So this is the center of the circle, which means that if I draw an axis from them to the center of the circle, it points that way, okay? From them to the center of the circle is just directly to the side. So you can imagine as they swing around, like they start right here and they're like, kind of like this, rope is up in the air, center of the circle is there, but as they swing, it's always going to be out the left side, okay? So this face that I drew here, it's actually on the other side of their head. Yeah, we should fix that, right? This is like the back of their head. This is hair. There we go. Isn't that lovely? They have triangle hair. It's beautiful, okay? So there they go. Swinging around that way, directly to their left is the center of the circle, everywhere in the swing, okay? So let's go down here and draw a free body diagram. There's the person. They just turned into a box. We said directly to the left is the direction that points to the center of the circle, so we're going to call that positive C. That defines the entire problem. You have no choice which way to make positive C. Why? Because the acceleration is pointing that direction, okay? So it's going to define where I'm allowed to put Y. I need it to be perpendicular to this, which means I could make it go down or I can make it go up. Those are my only options. So let's say that up is positive Y. And those will be my two axes. Notice C is already horizontal, so I'm not going to use X in this problem. It replaces X. let's stop there and see what questions you want to ask. Yes?
What if the person was moving the other way, where the pole would be on the right side of its hand?
If the pole was, so if they were swinging around this way instead of swinging around that way.
Okay.
If that was the case, then the C direction would be over here.
So why did you make C go that way? And how do we know that this person is moving?
Only because that's how we defined it at the start. They run this direction, grab the rope, and swing around. Okay? So here they're going, ooh, let's actually draw that in there. Let's get rid of this. They're swinging into the screen on the right and then out of the screen on the left. Okay? Ooh, we should get rid of this too, for the sake of confusion later. Okay? Anyone else? Anything? Nothing? C direction. The first time we've defined a C direction. What do you think we're going to do next on this diagram? Forces, right? We need to put in some forces. Name one force that's acting on this person. Gravity. Which way is gravity? Down. There we go, gravity. Name another force that's acting on this person. Tension. Yeah, the rope pulls along the rope's direction. So which way is tension pulling on the person? Which way is upwards?
So that angle theta, so
Yeah, so kind of off like that. Okay, the rope pulls right along its own direction, whatever that may happen to be. The rope is not pushing the person down that way. That doesn't make any sense, right? Ropes don't do that. That'd be weird. You grab a rope and it just throws you. It'd be terrible. Nobody wants that. Are there any other forces acting on this person as they swing through the air? No. They're not resting on the ground. They're not dragging on the ground. At least I hope they're not, right? To give us friction. And there's certainly no spring here at all. So we're out of forces. Notice, I never put in a centripetal or centrifugal force. Those are not forces. Okay? Got it? Yeah? Okay? What are we going to do next? That's our free body diagram. Now we write, yes, the net force, Newton's second law. We write the sum of the forces in the y direction and now in the c direction. No x direction in this particular problem. Okay, so we're going to start with those two equations and then go back to our diagram and fill in the forces that are there. Okay? Already looking at this diagram, we can see that one of them is in the y direction, one of them is in between directions, which means I need to break it into components, which is everyone's favorite thing to do. This is going to be angle theta, because if you look over at the diagram and imagine a straight up line, theta's there and there, alternate interior angles, which means I can write a component that goes straight up and a component that goes straight left. The one that's going straight up, what will it be? Yes, ft cosine theta, because it's the adjacent side, which means the other one will be ft sine theta. Someone thinks it's funny. Ft sine theta is hilarious. Yeah, can't help but agree. So let's see, in the y direction, the only thing that we have is that vertical force up and the vertical force down, okay? They're being subtracted. So let's see, in the y direction, I have ft cosine theta minus fg equals what? Is there acceleration vertically? No, if they're just swinging around at that constant angle, they're not moving up and down at all, right? So that is 0. Beautiful. Let's see, what are we given here? They gave us theta, m, and we know g. I think we can actually solve this side. So ft cosine theta minus mg for the force of gravity, and the only unknown in that equation is the tension force. So let's go ahead and find that. Ft is going to be mg over cosine theta, and that g is just in the way. Look at this. Come on, g. Gotta fix all of that. Now everything is ruined. There we go. So let's plug those numbers in and see what we get. Mass is 57, g is 9.8, and cosine of our angle, which was 26. Does anybody have that calculated? Anybody want to help? Anybody want to be friendly and help the teacher figure these problems out? Anybody want to be stubborn and not? Anyone who doesn't want to and wants to be stubborn, they're certainly not going to answer that question because double stubborn.
21.
621? That sounds pretty good.
Point 49.
49.5. Good. So we've got the tension. That's one thing we were able to find based on what's unknown so far. That should not come as anything new. Sum of forces in the y direction. In the c direction, looking back at my diagram, the only thing that points in the c direction is that top force. It's parallel to the c axis and points in the positive c direction. And that's all that's there. So I've got ft sine theta on the left side, and the acceleration, remember, is v squared over r. So now that I found the tension, I'm actually able to find the velocity. I can find the velocity from that. So let's rearrange this equation. We're going to have r times ft sine theta over m, and take the square root to get velocity. What's r? Where's the radius in my diagram?
The portion there.
From the pole to the person, right? Right here is the radius of the circle. Okay? So let's quickly find that because it wasn't given. But I do know theta and L. I know the hypotenuse and that top angle. So the sine of theta is going to be the radius over the hypotenuse L. So radius is L sine theta. And they said L was 2.4 and sine is 26. So I've got 1.05 meters for the radius. And now we have everything we need. Let's plug them in. 1.05 times 621.5 times the sine of 26, all over the mass, which was 57, and someone has that velocity. What is it?
How did you find the radius then?
From this triangle. So this, and that, and this side here is R. Anyone got the velocity? Yeah.
2.24 meters.
Seems good. 2.24. Thank you. 2.24 meters per second is how fast they're moving along that circle. What do you think? Yes?
How come it's not plus or minus?
Plus or minus? It is plus or minus. In both cases, we're looking at the magnitude. It's the same. It's the same constant velocity in both cases. The negative sign there really wouldn't mean anything. Okay? It's good though. Square root is always a plus or minus. And I'll let you sit with this for a second and see if you can come up with a question. Either you're totally confused or this is just so straightforward, like easy that you're happy. There's a question.
Is the radius not the same as ft sine theta?
Ah, I was waiting on something like that. Often people want to combine the two diagrams, okay? So this thing is physically what's really in the world, Okay, there's a rope, there's a pole, there's a person, there's a circle, and that circle has a physical dimension that is the radius. This diagram, though, is just the forces acting on the person. They don't occupy any physical space. They are just the vectors that are acting on this person and are not in any way related to like the physical things. So don't like layer the two diagrams and think that they're all the same. They're two separate things. Okay? The radius comes from physically what's happening. The forces are a completely separate thing of their own. Anyone else? Yeah.
We have problems where your y components and the force will not always equal to 0.
For a circle, I can't think of anything off the top of my head. Maybe, but I can't think of anything with circular motion. There are cases where the y direction will also actually be the c direction in our problem, and we'll flip that around. We'll have x and c instead of y and c, but I can't. Yeah, I can't say never, but nothing's coming to mind. Should we do another one? Should we do 2 more? Or maybe like 6 more? I don't know. So here's what we're going to do. I do have another example that's going to go right there, but just to divide things up a little bit, let's answer a few of these multiple choice questions first. And this one is terribly like what we just did, except instead of a person, we now have a ball. What direction does the net force on the ball point? Anybody have any votes? Anybody say 1, 2, 3, 4, 6, 5? So if we go back and look at what was essentially our free body diagram from before, it's the same, right? They use T and W for tension and weight. We had a component this way and a component that way. These two vertical ones, we already determined they cancel out, right? When I add them together, they give me 0. So those two add to 0. So the net there is just 0. But in the C direction toward the center of the circle, we could say that this other one, the one that points to the center of the circle, there is nothing to cancel it out. Why can I not spell today? It's all that's left over. And you can see it points to the center of the circle, which, well, looking at the options we have there, it points along the horizontal component of the tension force. The horizontal component of the tension force is all that's left, okay? So a different way of asking about the same sort of situation we had on the previous slide. Next is something that we've already talked about on these next 2 slides. You are a passenger in a car, and being a bad person not wearing a seatbelt. Wear your seatbelt, please. Make sure your airbags, if you have them, are working. Has anybody been hit in the face with an airbag? Anybody? Had the unfortunate situation where your airbag opened? No? Okay. I've heard it's kind of terrible. It's better than dying, but I heard it's kind of terrible still in its own right. So make sure they're working. Let's see, they're very hot. They'll burn you. So, and they punch you as well. But again, it's better than dying, so make sure they're working. The car makes a sharp left turn. That's what we described a few minutes ago. From your perspective, what do you feel is happening to you? You already answered this for me. What do you feel from your perspective is happening? Yeah, you feel like you're being thrown to the right when the car makes a left turn. However, what is really happening? What is the correct description is what is happening? And this takes it a little bit farther than what I described earlier. What are you actually feeling, assuming that you stay in the car because the door is closed? Which one are you not allowed to answer? Uh-huh. Anybody out there want to say one? Because if you want to say one, get out. Just go straight out this window. You're not even allowed to use the doors. I want you out the window. Okay? So one is not an answer. You're not allowed to say that something is a centrifugal force. No. Not to mention that's just not true. There is no centrifugal force. So what are these other ones? Well, it can't be both because number one's not allowed. Yeah, it leaves us with number 2. What's really happening is the door is keeping you in the car. Thank you, door, because you didn't have a seatbelt on, right? We already determined if the door is open, you're just going to keep going straight, and the car is going to leave, which means you end up out of the car, okay? So the door is the force that's actually making you take the turn with the car, okay? Just like on this previous problem here, there was this tension force component that points toward the circle in the middle. That's the thing that's making the ball go around in a circle. In this particular case, the door is the force that's making you go in a circle. So if I were to draw a free body diagram for you, this is you, there you go. And the car, we already know is going to like turn around to the left. Well, the forces on you are a few different things. You're gonna have a normal force from the seat, the gravitational force from the earth, and yes, there is a force from the door, which is the thing that points to the center of the circle, okay? It is the force that goes into this equation. So this would be F door equals MAC. Center of circle is over there, okay? So a variety of forces can act in the C direction. It's just that none of them are centrifugal or centripetal. They are other forces. Yes?
So the door, the force of the door would only work if I'm pushing against it.
Mm-hmm.
That's the only time it would work.
Yeah, so there is a Newton's third law thing there where you push on the door because you try to go straight, and the door pushes back on you with an equal but opposite force and allows you to keep going. Okay, good question. Anybody else? We're going to save the next one because I want to go back and work with the problem. Actually, flip over to the last slide. I just want to give you some nightmares going into the weekend. Has anybody looked at this? Have you seen this? Wow.
That was you.
That was me. I didn't draw this. This came from the publisher. Yeah, exactly. The publisher of, you can see right down here, Physics by Gian Coley, 4th edition. Yeah. So someone published a book through that, and that is the thing of nightmares. Yeah. Smile. Just keep smiling. I can't quite look away. We can make it a little more evil, probably. Got some teeth in here or something. That didn't get any worse, did it? Maybe bigger eyes, more hair on fire. I don't know what's happening. Anyway, let's go back. I just wanted to point that out because it's just terrible looking. We're not quite going to get to it today. So, number 2, a second example. Second example of circular motion. How about a car? Let's say that there is a road that's a circle, and on this circle is a car. And on that car is a person. And on that person is a coffee. I don't know. It seemed like there was a trend going there. Let's say that this is a flat, horizontal, circular road. Flat, horizontal, circular road. And I'm going to say that the car is going around the circle that way. So clearly there is a radius for the circle that would be right here. And at any given point, the velocity of the car is tangent to the circle. And then that velocity is going to keep changing directions because of something that we'll see in a minute. Something is making this car go in a circle. Now, there are forces on that car that I can't really draw based on that diagram because they're perpendicular to the screen, right? Gravity's going into the screen. A normal force from the road is coming out of the screen, so I can't really draw that. So let's say that this is my top view, and I'm going to change the view around to be a front view. So we're going to pretend the car is coming directly at us. So there's some headlights. Let's give this car some wheels. Oh, this is looking good. Boy, I've really got something going on here. And then, I don't know, that, and then maybe there's like a person in here. And they have a head and a neck. That's all. No, that's not good. It's really not good at all. You understand what it is. It's a car, right? It's coming directly at you. So, in this view, which way is it toward the center of the circle? So this is kind of like, let's go back in this other diagram. It's kind of like you're standing right here on the X, looking at the car coming directly at you. Which way is the center of the circle? Yeah, it's out the driver's side door, right? If you imagine like, well, the driver's sitting kind of, right there at that little dot. It's out the side with the driver. So this way is positive C. We're going to use a more fancy drawing for the car this time, for the object. It's beautiful. I want this car. I don't know what kind of car it is. What should we call it? It's a new. Well, it can't be a Tesla. That's taken. Maybe it should be the new. Someone else should make a new car. It's based on older Nusla. I don't like the sound of that at all. So let's see. From this, we've got a Y direction as well. So let's put that in there. The Nusla. I'm not driving anything called a Nusla. I would take a Tesla though. If anybody wants to volunteer, you know, your parents work for Tesla, I'll take 2, please. Thank you. Yeah. It won't help your grade because I'm not allowed to do that, but you know, I'll take all the gifts. Why not? They just won't do anything for you. Let's see. So, what forces do we have on our Tesla, Nusla, whatever it is? I don't know. Gravity. Good. Gravity points straight down. What else? Normal points straight up. And then what happens? Let me do this. Let's say that the road is just ice. Okay? Yeah, I know it's bad. It's all ice. It's not just ice, it's perfect ice. Perfect ice means no coefficient of friction, 0. Okay? So you're driving, you're like, the road is turning. I'm going to turn my wheel. And what's going to happen? Basically, yeah, that, right? You're going to keep going straight, but you're going to go straight as you rotate, right? And that's going to be kind of sad. So your car is just going to go wee like that. It's going to keep going straight, but because you turned your wheel, you send yourself into a rotation. Well, that's unhappy in every way. It reminds me of, I had a great experience on ice one time. I was in Tennessee. Not a lot of snow and ice happens there, right? So I guess I was being a little too creative on the ice and having a little too much fun and not careful enough. My brother and I were in the car. I was much younger than I am now. I should have been going slower, but what happened was we were traveling this way. You are all in my car now. Welcome aboard. Yeah, on the ice. Whee! So, yay. We had a right turn that was coming up. So I approached the turn. I put on my blinker to the right. I apply the brakes, and then the brakes don't work. Okay, so we're just kind of like, you know, sliding along or whatever, and then we start to spin. And we're like, whee! Like, we can't stop the car now. What's going to happen? It's like a narrow road, just one lane both ways, ditches on both sides, right? We're just swinging like this, and then we end up right here and come to rest. In the other lane, pointed the other way, ready to make a left-hand turn. I was like, well, that's convenient. So I took my blinker and went, left-hand turn, and off we went. I was like, well, that was fortunate in every way. There was no oncoming traffic or anything, and it just sort of worked out. But it was scary there for a moment, you know, as we just look at each other like, what's going to happen now? So you don't want that to happen here. You know, spins occur. So if you add the friction, just think what you just told me, the way that the car wants to go. It's going to keep going straight if there is no friction, just with rotation, but you don't really care about the rotation. Notice where it is now compared to the center of the circle. It's farther away from the center, right? You have left the circle. When the friction or whatever is going to help you fails, if there is no friction, you go straight, the circle leaves you, and now you're out of the circle, okay? So which way in this diagram on the right does the car want to slide? If there's no friction, which way does it desire to slip in this particular diagram? Remember, it has to go farther away from the center of the circle. So the car wants to slide this way. It would like to slide that way. If, and even if maybe there is friction, but maybe you're just going a little too fast around the curve, right? If I'm going around this curve, but I'm going too fast, well, if I leave the road, I'm not going to fall into the curve, right? I'm going to fall off the road out of the curve. The desire is for the car to leave the circle. So it wants to slide this way. The only reason it doesn't is because there must be friction pointing the other way that's keeping it from sliding. What kind of friction is that? Friction that's keeping it from sliding. Yeah, the thing I just described was static friction. You're like, but the car's moving. Yes, I'll address that in just a second, okay? Just talking about this C direction. If it stays in the circle, well, then it's always going to stay the distance R from the center, which means there's no motion in the C direction. If it goes too fast, it'll slide out of the circle, so there'll be motion in the negative C direction, which means that friction points the other way to keep that from happening. Okay, that is static friction. As soon as it starts sliding, so if you're driving too fast, as soon as it starts sliding, you've overcome static friction. And we already learned that kinetic friction is less. So then it's kind of like a snowball effect, right? You're already sliding off the road, and now you have even lower friction than what you had before. So then all is kind of lost, okay? Bad situation. So if you're thinking like the car's moving, how can I have static friction? That friction that you're wanting is happening in the other direction, and it's actually pointing towards you, okay? We're not gonna deal with this type of friction. It's called rolling friction, and it's the same friction that basically allows me to walk, right? If I had no friction under my feet, I would try to take a step and my foot would just do that, and I'd be like, well, that was irritating. Let's try the other foot. And I would just like stand here all day and just do this because I wouldn't be able to go anywhere, okay? If there was no friction on the road in this direction, the wheels would just spin. They wouldn't have anything to push against, okay? So there is a friction that actually helps you go forward, that points in the same direction of your motion, okay? That is rolling friction. It's actually less than kinetic friction, which is why wheels are nice, right? It reduces the friction even further. So it's essentially negligible in this problem, so we're not going to worry about it. We don't learn about that third type of friction in this course. Does that satisfy a little bit? Maybe? We're only worried about being able to drive in a circle, So this is our free body diagram. This is it. It's this friction force that forces me to stay in the circle and keeps me on the road safe, okay? So let's write out some equations in the y direction. Is it accelerating in the y direction? No. It's not moving up and down. No up and down motion. So I've got normal force, that's vertical, up, and then gravitational force down equals 0. So we could really just sort of finish this out. mg, and that is our final equation in the y direction. Normal minus gravitational equals 0. In the c direction, I only have the one force. So the sum of forces in the c direction equals MAC, and my one force is static friction. Don't forget that acceleration is v squared over r. And now things get interesting. There was an unusual aspect to static friction. Do you remember what was weird about static friction? Anybody?
So it's got like being more than or less than equal to.
Yeah, there was some less than stuff in there. It wasn't a fixed value, like it varied, right? You can imagine, like, if the car's just stopped, is there any friction sideways? No, like it's just sitting there. There's no desire for it to slide out of the circle. If it goes a little fast, right, you can imagine there's a little bit of static friction that's holding on. If it goes faster, static friction has to hold on more. There's some velocity where maybe I've reached all the friction that's possible. And if I go any faster, I'm gonna fall off the road, right? I'm gonna start to slide, I'm gonna leave the road, things are no good, okay? So what we're going to try to do is figure out the maximum velocity. At the maximum velocity, that's when I'm going to have maximum friction. And that's when I can say that the static friction is equal to mu s times Fn. Remember, that's the maximum friction equation. It ranges from 0 up to that value. So if I use that equation for static friction, that means I'm going to be solving for the maximum velocity for this particular road. So let me go ahead and give you some numbers just because it'll make you happy to have something to actually solve for. Let's see. Let's say that the radius is 45 meters. The mass of the car is 1,200 kilograms. And the coefficient of static friction is 0.82. And let's see if we can find the velocity. So, in this equation, we've got mu s times Fn equals mv squared over r. And from this equation, I can say that Fn is equal to mg, and then I could plug that in over here. Which means that now I have mu s times mg equals mv squared over r. And then notice the masses cancel out. Is that weird? Is it weird that the masses cancel out? It's funny that the masses cancel out. Think about it. When you've seen highway signs where maybe you approach a curve and there's a new speed limit that's lower, well, someone's done these calculations and they've said, like, if they go faster than this, they might slide off the road. And then they even deal with worst case scenarios, right? What if it rains and the friction drops? What's the fastest you can travel and be safe? So you might see signs that are like, you should travel this fast when raining versus a normal speed. But what you don't see is, like, if you're driving a compact car, please go this speed. If you're driving an SUV, please go this speed. If you're driving a midsize, please go this speed. The mass doesn't matter, okay? The mass there doesn't matter. If you're thinking about, like, tractor trailers, trucks and stuff, there's more going on, right? It's like two parts that are like this, and they can tip over. Like there's a whole lot of other situations for those on the road that's more than just their mass. But you don't see different speed limits for different masses of cars. So it makes sense that would cancel out. Let's see, let's solve that for the velocity. We've now just got the square root of us times GR. And we know all of those. So that's 0.82 times 9.8 times 45, and you should get about 19 meters per second. 19 meters per second.
Why doesn't the mass matter again? I mean, on the road?
Why doesn't it matter? In this particular case, and you'll see that it matters a little more in the next example that I'm looking at. In this case, we have a perfectly flat road, which isn't terribly realistic. Like a flat, curved road isn't generally how they're built. And you can see that the normal force is exactly equal and opposite to the gravitational force. So any impact that the mass is having is being directly canceled out. It's being pulled down and then supported equally. And now it just has no play on the problem at all. When you see the next one, the mass will come into play and it looks a little different. Anyone else? Yeah.
Are those still inside the square root?
Oh, all of that is inside the square root. My fault. My square root just kind of got messy and ended for some unknown reason. Okay. Let's step this up one other notch to something a little bit more realistic. Okay. Typically, if someone is building a curve into a road, what do they do to the road? They tilt it a little bit. They bank it. Okay. So let's put a new slide in here and work this exact same problem, except let's make it a banked curve. Add a page. That page. Beautiful. So let's say we have a banked curve. And we already know, like, it's banked probably to make it safer, which means that it should allow for higher velocities and still stay on the road, okay? So we're gonna see that we're just gonna give it maybe a small bank and just see that from 19 meters per second, we should get something that's a little bit higher. It should be a little bit safer, okay? So if we were to draw that, maybe again from the front of the car, let's say the car is here. Oh, there's our person again. And we'll put some wheels down here. There we go, because we don't want the bottom of the car just sliding, even though it really appears like it is. Just deal with it. And if it helps a little bit, maybe down here is like the flat ground. And maybe this is a curve that just goes all the way in a circle and it's banked everywhere. So that over here is another bank. And if this were the case, imagine maybe the car comes out like this and the road curves around. And then over here, the car would go into the screen on that side, okay? So just imagine a circle like that, except all the curves are banked. So if the car is traveling in a circle that far above ground level on a banked curve, where's the center of the circular motion? Tell me when to stop. Right here, the center of the circular motion. There's some noise for this. So we've got some down here, some up here. I'm moving around. Whoops. Come back, laser pointer. Ooh, some noise for there. Okay, so is it here, here, or down here? Here. What's the car doing again? It starts here, comes out of the screen, and then goes back into the screen over there, right? That surely seems to indicate that the circle is kind of like this. It's hard to draw, but you get the idea, okay? It's making a circle a little bit above ground level because it's sort of up the side of the bank a little bit. So the center of the circular motion is there. Center of circular motion. Which means that from the car's perspective, the C direction is sort of directly over that way. It points to the center of the circle. So let's hold that in mind and draw a free body diagram. So let's see, down here somewhere, car on a slope. We just determined that the C direction is straight over this way, positive C. Where's the Y direction? Remember, it has to be perpendicular. The axes have to be perpendicular. So really, one of only two options is for it to be here. Okay? You might want it to be perpendicular to the slope, but if I do that, it's not going to be perpendicular to the C axis, and my axes have to be perpendicular. Okay? So keep in mind, when working these problems, the C axis defines the whole problem. Where is the center of the circle? Find that and point an axis at it. Once you have that, it restricts where Y can be because it has to be perpendicular. If you start by saying, like, I'm just going to pick Y to be somewhere, you're going to have problems, okay? Make sure that your C axis points to the center of the circle. Once we do that, name a force that's acting on the car. Gravity. Gravity points down. There's down. Yay. Normal force. Which way is it? It is perpendicular. Yeah, perpendicular to the slope. So there's my normal force. Now what? If the car goes too fast, which way does it want to slide? Imagine driving around that little bowl faster and faster and faster and faster and faster and faster and faster. Which way will the car slide if it's going too fast?
To the left.
To the left?
To the right.
This way? I don't think it can go into the road. That sounds sad. To the right? If it goes too fast, I don't think it's going to come like flying off and tumble that way. What happens if you have a drink and you just swirl it around? It goes up the sides, right? As you swirl it around. That's kind of what's happening here. You swirl the car around, it's going to want to slide that way. Okay? As it goes faster and faster and faster, it wants to slide this way. If too fast. Okay? It wants to slide up and out of the circle if it's going too fast. Which means which way is the friction that's keeping that from happening? Yeah, it has to be this way. Okay? So that's my static friction force. So we're doing 3 problems today. We're going like easy, medium, hard. Okay, you're kind of getting the full gamut of problems here. Yes?
Okay, I'm kind of confused about that force thing, because like because the road is kind of like, it's like a weird like funnel
Yeah.
donut kind
Yeah.
of thing. And if you drop something into a funnel, it's going to go towards the center.
So we are, first of all, if you imagine the car was stopped. If the car is stopped, it wants to slide this way. Agreed? If it's just sitting there on a slope, like it's only friction that's keeping it from just sliding straight down the slope. Okay? But if I'm driving in a circle and driving too fast, I don't have a tendency to get closer to the center of the circle. I have a tendency to leave the circle by going straight. Okay, so what I would like to do, if we were to look at this again top down, the circle's like this, we're driving around this way. I want to go straight, which means I want to get farther away from the center. Farther away from the center here, I don't really have an option to go this way because of the road, so I'm kind of forced to try to slide up the edge. Up the slope is farther away from the center of the circle. So yeah, there are two cases. If you drive too slow, there's a chance maybe you want to slide the other way, but we're looking at the extreme of going too fast. Okay? Let's see. What's this? It's gone. And now you can already see, like, ooh, the forces are more complicated this time. Two of them need components. So the angle of this incline, let's say that this is angle theta, and let's say that theta is 10 degrees here, just a little bit of a banked curve, not too much at all. Where can I put the theta in my diagram? Ugh. Any thoughts?
Between friction force and gravity, because the friction force is basically your hypotenuse.
Friction force is the hypotenuse. I agree with that. Let's see.
Oh, then,
Alternate interior.
Alternate interior. You have another thought? What about, you're about to say something? No? You have a thought?
I think you can put it, like, so if you have like the friction force and the gravitational force, and then you draw a horizontal, you can put it like in that little corner between the horizontal and the friction force.
Like here?
Yeah, because it's the same triangle.
I would agree that that's theta. Yeah.
I don't know how that helps at all.
I'm not sure how that helps either. Let's see. I'm going to, let's draw a few things up top here. Like, so we have gravity that's straight down, and then we said that friction force is going that way. So I agree that theta sits right inside there. So where else is theta?
Between normal force and the friction.
Oh,
Between normal force, so all of this,
no, between the friction force and the horizontal.
friction force, so here.
Yeah.
Yes, that would also be theta. So those are alternate interior angles. The bottom one we get from, well, sort of just draws that way. The slope is there, then an alternate interior angle. There's one other angle in there that's also equal to theta. And it'll help us with the normal force.
Between the y and the normal force.
Yeah. So there's a 90-degree angle, and there's a 90-degree angle, okay? And they share this one in the middle, which is not theta, which means that this one over here also has to be theta. Ugh. Geometry, right? Yeah. All at once, geometry.
Yeah.
You're supposed to make noises. Right? Ooh, physics, wait a minute. No, geometry, yeah, there we go. Okay, I'll do it myself. So here we go, let's put in some components of forces. So we can draw a triangle here. It goes over there. This side will be Fn cosine theta. This side will be Fn sine theta. And we can draw another triangle down this way. This side will be force, friction, static, sine theta. And this side will be force, friction, static, cosine theta. Fun. Two different vectors that we have to break into components. And now we have just a really big mess. So I've got a vertical force here that's in our y direction, a negative one in the y direction, and then I've also got this one hiding over here that's in the negative y direction. So if I write out the sum of forces in the y direction equals MAY, it's not moving up or down in that direction, it's staying at that same level. We've got Fn cosine theta minus the gravitational force minus F friction static sine theta equals 0. Well, that's a long equation. One is up, two are down. One is up, two are down. And if you look through that equation, there's only one unknown. So let's go ahead and work through that. So normal force cosine theta minus mass times gravity minus the coefficient of static friction times the normal force sine theta equals 0. just plugging in all the little mini equations for things that I have equations for. And then I'm going to solve that for the normal force. So let's see. Let's get everything with just the normal force on the left-hand side by itself. And we'll move the mg over to the other side. And then factor out the normal force. And then solve for the normal force. Mg over all this stuff. Yay. We have m, we're just going to use what we had on the last slide. Same mass of the car, g is known. Theta, we said, is going to be 10 degrees, and the same coefficient of static friction. So let's plug that in. I do not have this number, so I actually need your help. I'm not lying this time. I'm not like, somebody calculate it for me when I have it right here. I just want you to do something. This time, I literally don't have the number, okay? I need help. So let's see, this is 1200, 9.8, cosine of 10 minus 0.82 sine of 10. Help, 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 help. So we can finish this problem in the last 4 minutes.
Hey, when were we given?
Hmm?
Oh, we were using the same.
Yeah, we're going to use the same numbers, the same car. We're just putting it on a banked curve this time. Now you're stalling. You're trying to make the clock run out.
It's just like a really big number.
It's pretty big.
Like really big?
Pretty big.
I have like 13,000.
13,000 something? Yeah. 13 what?
959.
959. Okay, sounds good. We're going to use that over in the c direction to again find the velocity maximum. So MAC. And in the c direction, I have Fn sine theta plus F friction static cosine theta equals mv squared over r. So we have everything we need there to solve for the velocity, and then we'll be done for this problem and for the week. So Fn sine theta plus coefficient times the normal force cosine theta equals mv squared over r. Ooh, algebra fun, right? So let's see, r over m times all of this stuff. Oops, that's a cosine. And we have to take the square root of all that, and we get v. And somebody's going to calculate that before we run out of time. I know, you can do it. We have r from the previous problem, it's 45 meters, the mass of the car is the same. We just found the normal force, we know theta, we know mu. You know how to take a square root by pushing a button. And you should get something bigger than 19 meters per second because it's a banked curve. You should be able to travel a little faster and still stay in the circle. Not a whole lot faster, but a little faster. It's 20 something. But I don't know what. Hell. All your classmates want to leave. I want to leave. 22 or 23, somewhere in there. Anybody?
22.6.
22.7.
22.7.
Seems about right. Depending on how you round, somewhere in that vicinity. Circular motion, we did it. We'll answer a few multiple choice questions at the start of class on Tuesday, and then start chapter 7. Goodbye, have a good weekend. I'll see you in many days.